In this video, I'm going to give you an elementary introduction to linear algebra. Linear algebra involves words like matrix and vector. So first I want us to use these words in a setting you're probably already familiar with, ordinary arithmetic. So let's start by asking the question, what is a vector? We'll begin with the most basic case, which is just thinking of vectors as ordinary numbers. So let's draw a number line. And I'll represent the number with an arrow that points from 0 to 2, just like this. But instead of writing 2, I'm going to write it with this box around it. I didn't really need to write a box around it. This is literally just the number 2, but I'm going to use the box notation because that's what we'll use when we move to higher dimensional vectors. Now this number 2, it's also an example of a vector, but it's just a one-dimensional vector. And here, the one-dimensional part, it just means that it's described by one number. Now let's make arithmetic unnecessarily confusing by using the language of linear algebra. We want to consider what happens to vectors, which in this case are just the same thing as numbers. What happens to vectors under multiplication? So we'll build a number line. And we're going to look at the vector 2. Now I'm going to multiply by the number 3, except I'm also going to draw a box around 3 and call it a matrix. Okay, so what do you get when you take the vector 2 and you multiply it by the matrix 3? Well, it's just 3 times 2, so you get 6. But what you get is the vector 6. I'll show you what I mean. At the bottom, we have the vector 2. We think of the matrix 3 as stretching the vector out so that it is now the vector 6. What else can multiplying by matrices do in one dimension? Well, since they're literally just numbers, they can do anything multiplying by numbers can. For example, instead of stretching out, we could compress the vector, or we could flip the vector to the opposite direction. Now, using our intuition of a vector as being some sort of arrow and a matrix as a way to transform the arrow, let's jump to 2 dimensions. For 2-dimensional vectors, instead of just a number line, I'll need a whole plane. And now I'll draw some vector in the plane. We're going to describe the vector with a pair of numbers corresponding to its value on the x-axis and its value on the y-axis. So we write this as 3, 1, where the x-axis value is on top and the y-axis value is on the bottom. It's okay to write the y value on top and the x value on bottom, you just need to be consistent. What I mean is that if I draw another vector, I'll also put its x value on top and y value on the bottom. Again, let us ask the question, what does multiplication do to vectors? We'll have a vector, which I accidentally wrote as 2, 1 instead of 3, 1, and we'll multiply it by some matrix T. Don't worry about what I mean by matrix right now, I'll show you in a bit. Let us see a few things we can do to a vector. So we make a plane and draw the vector 3, 1. In the one-dimensional case, we were limited. We could only stretch, compress, and flip. But now there are new things we can do to vectors. For example, we can rotate vectors. And we can also do the transformations from before, like compressing and flipping. Here is where higher dimensional matrices differ from the first matrix we saw. We can consider what happens not just to one vector, but to pairs of vectors. What ways can pairs of vectors be transformed? It is possible that they get transformed the same way. For example, perhaps they both get rotated, or perhaps they both get flipped. But this doesn't have to be the case. The way one vector gets transformed could be very different from how the other vector gets transformed. It could even be that a transformation changes one arrow but not the others. Matrices are the ways to perform these transformations, so let us ask, what is a matrix? In the one-dimensional case, we had the vector 2 and the matrix 3, and when we multiplied, we got the vector 6. We will have the vector 2, 1. Now let's look at the two-dimensional case. We'll have the vector 2, 1, and now a matrix will be any set of numbers. And we're going to multiply and end up with another vector. The way we multiply is we go across the matrix and down the vectors like this. Let us look more generally at a matrix. Notice that it has 2 rows and 2 columns, and we call this a 2 by 2 matrix. And now I'll show you how to multiply any two-dimensional vector by a 2 by 2 matrix. Now let's go to vectors in any dimension. We have an n-dimensional vector, which is just a collection of numbers like this. And we can even add vectors of the same dimension. We just add them term-wise like this. I'll show you an example in the two-dimensional case. And now let's look at general n by n matrix, where m means rows and n means columns. And we can draw it out like this. We just need to put n columns and m rows like this. We can also add matrices term by term, similar to how we add vectors. Again, I'll show you an example. Now let's look at general multiplication. In the general case, we need the number of columns of the matrix to match the number of rows of the vector. Otherwise, multiplication won't work. There's no restriction on the number of rows of the matrix, but this will just be the number of rows of the outputted vector. Here's an example of multiplication with a non-square matrix, and we just go across the matrix and down the vector like before. Finally, I want you to start thinking of systems of equations in a different way. Let us begin with the most basic system of equation, the one-dimensional system. I could ask you to find the solution to 3x is equal to 6. But now let's fancy it up with linear algebra. So I'll draw a box around 3 and call it a matrix, and I'll put a hat on top of x and call it a vector, and a hat around 6 and call it a vector. And now I'll ask you the exact same question, but in a more complicated manner. Find the vector x such that 3x is equal to 6. And of course the answer is still just 2. Now we'll look at a system of equation with two variables. But like before, we'll reformulate solving this system into the language of linear algebra. So we'll call these things vectors, and I've written it suggestively where we can decompose the left into this matrix times this unknown vector. And if we call this matrix T, and this vector v. Now I'm asking you to find the vector v such that TV is equal to 8, 3. Okay, that's where I'm going to end this video.